Hello everyone, this is Nitesh Khanal from Department of Physics, Namchi Government College, South Sikkim, Kamrang. And today I am here to discuss on the topic semi-empirical mass formula. And this assignment is submitted to Head of the Department of Physics, Namchi Government College, Dr. C.P. Khatiwada. So here are the contents. At first, we will discuss about types of nuclear model, then the liquid drop model, and then we will deal with semi-empirical mass formula, and we will see the formula itself, then the Pauli exclusion principle and the various terms which includes volume energy, surface energy, Coulomb energy, asymmetry energy, and pairing energy. So here are the different types of nuclear models. At first, we have liquid drop model, which we will study later on in detail in the next slide. In second, we have forming gas model, followed by cell model, and then collective model, superfluid model, Nelson's model, Thomson model, Rutherford's model, Bohr's model, Sommerfeld model, vector atom model. These are the different types of nuclear model, but we only need a liquid drop model. So in the next slide, we will talk about that. The liquid drop model. In this slide, we will discuss about the liquid drop model. In nuclear physics, the liquid drop model treats the nucleus as a drop of incompressible nuclear fluid of very high density. This theory was first proposed by George Gamow and then later developed by Niels Bohr and George Archibald Wheeler. The nucleus is made of nucleons, that means it contains protons and neutrons, which are held together by the nuclear force. This is very similar to the structure of a spherical liquid drop made of microscopic molecules. This is a crude model that does not explain all the properties of the nucleus, but it does explain the spherical shape of most nuclei. In nuclear physics, the semi-empirical mass formula is also called Weizsäcker's mass formula or Pitt-Weizsäcker mass formula. It is mainly used to approximate the mass and various other properties of atomic nucleus from its number of nucleons, that is, protons and neutrons. As the name itself suggests, semi-empirical, it is based partly on theory and partly on empirical measurements. This theory is based on liquid drop model, which was proposed by George Gamow, which can account for most of the terms in formula and gives rough estimates for the values of the coefficients, which we will discuss later on. It was first formulated in 1935 by German physicists Carl Friedrich and von Weizsäcker. So here is the formula. Let A be the total number of nucleons, Z the number of protons, and N the number of neutrons, so that we get mass formula A equals to Z plus N. The mass of an atomic nucleus is given by M equals to Z MP, MP is the mass of proton, plus N Mn minus Eb by C square, where Mp and Mn are the rest mass of proton and neutron respectively, and Eb is the binding energy of the nucleus. The semi-empirical mass formula states that the binding energy will take the following form: Eb equals to AV A minus AS A to the power 2 by 3 minus AC Z Z by 1 divided by A to the power 1 by 3 minus AA A minus 2Z whole square divided by A plus minus del A comma Z. Each of the term in this formula has a theoretical basis, as will be explained below. The coefficients AV, AS, AC, AA, and a coefficient that appears in the formula for del AZ are determined empirically. The mathematical analysis of the theory delivers an equation which attempts to predict the binding energy of a nucleus in terms of the number of nucleons in it. This equation has 5 terms on its right hand side. This corresponds to a volume term, a surface term, the electrostatic term, the asymmetry term, and a pairing term. In the previous slides, we talked about Pauli exclusion principle many times. So in this slide, let us see what it exactly is. It states that no two electrons in an atom can be at the same time in the same state or configuration. It was proposed by Austrian physicist Wolfgang Pauli in the year 1925 to account for the observed patterns of light emission from atoms. The exclusion principle subsequently has been generalized to include a whole class of particles of which the electron is only one member. If we consider the sum of the following 5 types of energy, then the picture of a nucleus as a drop of incompressible liquid roughly accounts for the observed variation of binding energy of the nucleus. At first, we have the volume energy. When a group of nucleons of the same size is packed together into the smallest volume, then each interior nucleon has a certain number of other nucleons in contact with it. Here we can see that in the volume term, if we consider any nucleon right here, there are other nucleons in its surrounding which it is in contact with. And second, we have the surface energy. A nucleon at the surface of a nucleus interacts with fewer other nucleons than one in the interior of the nucleus, and hence its binding energy is less. Again, we can see the surface at the nucleons is in contact with less number of nucleons than the nucleons at the center. Next is the Coulomb energy. The electric repulsion between each pair of protons in a nucleus contributes towards decreasing its binding energy. Protons being positive in charge, when two protons come close to each other, repel, and it leads to decreasing of binding energy. Here we can see that the electrostatic repulsion between protons leads to the decrease in binding energy of the nucleons. Next is the asymmetry energy. It is also called Pauli energy, an energy associated with the Pauli exclusion principle, where it not for the Coulomb energy, most stable form of nuclear matter would have the same number of neutrons as protons. To be stable, an atom must contain same number of neutrons and protons. Since unequal numbers of neutrons and protons imply feeling higher energy levels for one type of particle, while leaving lower energy level vacant for other type. Next is the pairing energy, an energy which is a correction term that arises from the tendency of proton pairs and neutron pairs to occur. So here are the different terms. At first we have volume term, then surface term, Coulomb term, asymmetry term, and pairing term. Volume term. The first two terms describe a spherical liquid drop of an incompressible fluid with a contribution from the volume scaling with a to the power 2 by 3. The first positive term is known as the volume term, and it is caused by attracting strong forces between the nucleons. The strong force has a very limited range, and given nucleon may only interact with its direct neighbors. Therefore, the term is proportional to A. The next term is the surface term. The term a to the power 2 by 3 is known as the surface term. This term, also based on the strong force, is a correction to the volume term. So this term is a correction to the volume term. The volume term suggests that each nucleon interacts with a constant number of nucleons independent of A, while this is very nearly true for nucleons deep within the nucleus. Those nucleons on the surface of the nucleus have fewer nearest neighbors. Justifying this correction, this can also be thought of as a surface tension term, and indeed a similar mechanism creates surface tension in the liquids. If the volume of the nucleus is proportional to A, then the radius should be proportional to A to the power 1 by 3 and the surface area to A to the power 2 by 3. This explains why the surface term is proportional to a to the power 2 by 3. The term a plus x to the power n equals to ac z minus 1 by a to the power 1 by 3 is known as the Coulomb or the electrostatic term. This term describes the Coulomb repulsion between the uniformly distributed protons and is proportional to the number of proton pairs z square by r, where r is proportional to a to the power 1 by 3. This effect lowers the binding energy because of the repulsion between charges of equal sign. Asymmetry term. The term 4 alpha a minus 2z whole square whole divided by a is known as the asymmetry term. The theoretical justification for this term is more complex. Pauli exclusion principle states that no two identical fermions can occupy exactly the same quantum state in an atom. At a given energy level, there are only finitely many quantum states available for particles. What this means is the nucleus is that as more particles are added, these particles must occupy higher energy levels, increasing the total energy of the nucleus and decreasing the binding energy. Note that this effect is not based on any of fundamental forces, it is only based on the Pauli exclusion principle. Protons and neutrons, being distinct type of particles, occupy different quantum states. One can think of two different pools of states, one for protons and one for neutrons, as here shown in the figure. Now, for example, if there are significantly more neutrons than protons in a nucleus, as in the first case, some of the neutrons will be higher in energy than the available states in the proton pool. If we could move some particles from the neutron pool to the proton pool, in other words, change some neutrons into protons, we would significantly decrease the energy. The imbalance between the number of protons and neutrons causes the energy to be higher than it needs to be. For a given number of nucleons, this is the basis for the asymmetry term. Now let us see what nuclear binding energy is. Nuclear binding energy is the minimum energy that would be required to disassemble the nucleus of an atom into its component parts. These component parts are neutrons and protons, which are collectively called nucleons. The binding is always a positive number, as we need to spend energy in moving these nucleons attracted to each other by the strong nuclear force away from each other. The mass of an atomic nucleus is less than the sum of the individual masses of the free constituent protons and neutrons. According to Einstein's equation, E equals mc square, the missing mass is known as the mass defect and represents the energy that was released when the nucleus was formed. Pairing term. The term del A, Z is known as the pairing term. This term captures the effect of spin coupling. It is given by del A, Z equals plus del naught when Z, n even and A even, 0 when A is odd, minus del naught when Z, n odd and A even. This term captures the effect of spin coupling. Nuclei with an even number of protons and even number of neutrons are very stable. On the other hand, nuclei with an odd number of protons and neutrons are mostly unstable. So this is the pairing term. So now with the aid of Witt-Wiesacker formula, the binding energy can be calculated very well for nearly all isotopes, which is the application of this formula. This formula provides a good fit for heavier nuclei. For light nuclei, it provides a poor fit, and it is its disadvantage. The main reason is that formula does not consider the internal cell structure of the nucleus. So thank you everyone.